Okay, in this video lecture, we're going to go over some of the equilibrium problems that we ignored in class for Chemistry 108, Introductory Chemistry 2. Let's go to the first problem here. We're given a reaction here, N2O4 goes to 2NO2. Given some information, we're given what Kc is. We're given 1 liter flask, 0.1 molar. Initially, so we're given initial concentration, and what we want is the concentration of NO2 at equilibrium. All right, looks like we should use the procedure used in a textbook and also explained in class, and that's the ICE table. So let's write up here N2O4, the reaction. It's been in equilibrium with 2NO2. Okay, and here we're going to make our table. So we'll have our initial concentrations, our change, and our equilibrium concentration. All right, well, let's go back, see if we can get some information from the problem. Go back, there we go. Let's look, we're looking for Kc, or we're given Kc, so let's express concentrations in terms of molar. Okay, 0.1 mole in a 1 liter flask. Looks like the concentration there is 0.1 molar. And initially we have none of this. Oh, looks like pretty straightforward here. It'll be minus x, and there'll be a 2x here, plus 2x. That should be an x, plus 2x. And let me use the eraser function. Yeah, that's kind of cool. Okay, so plus 2x. That's a 2 there because there's a 2 there. At equilibrium, our initial concentration minus the change, and here is our initial concentration, or sorry, initial plus the change. Initial plus the change, this is just 2x. We'll write down what the equilibrium expression is. Kc will be equal to the NO2 concentration squared divided by the N2O4 concentration. Kc, given in the problem, was 0.36. And let's go ahead and substitute what the equilibrium concentrations are in this expression. This would be 2x. The whole quantity is squared. Don't forget to square the 2 also. And down below we have 0.1 minus x. So we've expressed this equilibrium expression in terms of an unknown concentration x. If we know what x is, we can figure out what the equilibrium concentration of NO2 is and what the equilibrium concentration of N2O4 is. So the rest is just trying to find out what x is. What we discussed in class today was the ignore X approximation, or as Tro and other introductory chemistry texts call it, the successive approximation. That's where if you have X being subtracted or added to a number, you just let X equal 0 in that case. When X appears by itself or multiply by a number, you keep that value of X. So let's go ahead and do the successive approximation approach. We'll ignore x right there. So our equation becomes 0.36 is equal to 2x, quantity squared, divided by 0.1. And when we ignore x, typically what we get is a simpler equation to solve for x. Let's go ahead and do that. I'll just skip a few steps, intermediate algebraic, and just write down just what x is equal to. You can check this if you want. 0.36 times 0.1 divided by 4 raised to the square root, or raised to the 1/2, the square root of that. And we put this in our calculators, we find that x is equal to 9.49 times 10 to the minus 2. Okay, now in the successive approximation approach, we take this value of x and substitute it in where we ignored it before. We ignored it before right there. Or if we look at this equation, we ignored it right there. So x is equal to 0.36 times 0.1. But remember, we ignored it here, but now we have a better value for x. Essentially, by ignoring it, we put x equal to 0. With x equal to 0, we get this value of x. Let's now put that in. That's a better value of x. 9.49 times 10 to the minus 2. This whole quantity, I have to divide by 4. Oh, sorry about that. We're going to have to learn how to use this graphics tablet here. Divide by 4 and take the square root of that. And x for the second step is 2.14 times 10 to the minus 2. Oh, well, that's a big change there. It doesn't look like the successive approximation is going to converge very rapidly. Well, let's do one more step. Let's now put this new value of x into where we ignored it. So x, without showing the calculation, 8.41 times 10 to the minus 2. So 8.928 looks like it's oscillating around a lot. So in this particular case, it doesn't look like the successive approximation is a very good approximation. Why is that? Well, let's go back here. The reason is that the equilibrium constant is fairly large compared with these concentrations here. And the successive approximation really works well only when the equilibrium constant is small, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, something like that. Here, Kc, or equilibrium constant, is 0.36. So that means you got equivalent amounts of reactant and products, and x is not going to be small compared to what you're subtracting it from, the initial amounts of reactant or product. So that's why it doesn't work. So let's bite the bullet and go ahead and do the quadratic formula. So if we go back to this equation here and multiply everything out without doing that explicitly, I'll let you do it. I'll just write down what the result is. The result is 4x squared plus 0.36x minus 0.036. So this is ax squared plus bx plus c. The quadratic formula, x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Let's plug in what a, b, and c are. Minus b minus 0.36 plus or minus the square root of b squared, 0.36 squared, minus 4 times a is 4, 4, times c, don't forget the minus sign, minus 0.036. And we have to take the square root of that and then divide by 2 times a, which is 4. And you multiply this out, divide, square root, etc., etc. Remember, it's a quadratic equation, so we'll get two roots, the plus root and the minus root. The plus root is 0.06. That's the plus root. Plus root means we took the plus here. And the minus root is minus 0.15. So when you solve an equilibrium problem using the quadratic formula, you always get two roots, but one root will make sense and the other won't. Which root does not make sense? Turns out the negative won't make sense. Remember that root, minus 0.15. Let's go back up here to the ICE table. X is minus 0.15. You multiply that by 2, you get a negative number for equilibrium concentration. That's not going to work. So what we can safely say is that this is not reasonable because it gives a negative concentration. So we're going to take this positive root. All right, let's go ahead and do that. So our two reactants, so N2O4 concentration Remember from the ICE table? Well, maybe you don't, so let's go back here to the ICE table. Equilibrium concentration N2O4, 0.1 minus X, and we found out that X is 0.06. So this is 0.10 minus 0.06. So the concentration is 0.04, and the units here are molar because we're using Kc. Then the concentration of NO2, that will be 2x, so that'll be 2 times 0.06, so it's 0.12 molar. So that's how you do that problem. We started out with a successive approximation, but we found out that it didn't work, and the reason was this was large, the Kc was large. So we went and used the quadratic formula. Okay, now let me make two additional points. Remember in class when we started working these problems, I said that in the future you probably will not need to actually do these calculations because, for instance, there'll be a phone app, or you'll be wearing your Google glasses and talking into a microphone and say, solve this equilibrium problem. Well, Professor Jones, who's now Dean Jones, and I, about 15 years ago, were working on a supplemental CD-ROM for a leading introductory chemistry text, and we developed such a program. And here it is, the Equilibrium Calculator. All right, looks like I already put in some numbers here, but essentially what you do is you just put in coefficients and concentrations initially, click this button, and then what's given by this calculator is equilibrium concentrations. So what I put in here is, let's let this A be the N2O4. So you have 1 N2O4 with the initial concentration of 0.1. Remember that was from the ICE table, so we're just putting into this equilibrium concentration our ICE table. So 0.1, that's the initial concentration. And then the coefficient is 2 here, initial concentration 0. You click, and the equilibrium constant, 0.36, 0.36. Click this, lo and behold, there's your equilibrium concentrations. And these are the ones we just calculated. Unfortunately, we're not yet there in introductory chemistry pedagogy, so you still have to know how to solve these by hand. But my prediction is in 10 years, solving these by hand will be like solving a problem today with a slide rule. Now the second point I want to make is, well, remember when we did the successive approximation, we calculated this with a calculator and calculated this with a calculator and so on. Well, you know, you don't have to do that because, so here we are. What we're going to do is to program into Excel that equation that we used. We tried successive approximation and it didn't work, but let's just see if we can, well, actually it would have worked if we had spent a lot of time doing those calculations, but it didn't converge very well. But we can actually program Excel to do those calculations for us very rapidly. So let's go back and take a look. Here's the equation. Well, actually, let's go to the next one. This is the equation. So here's the value of x right here. And depending, we eventually got a value of x. We solve, we get another value of x. We put it back in there. We get another value of x, put it back in there, and so on. So let's just take this equation here and program it into Excel. All right. So we'll put it right here, equal the square root of, and go back here, it's 0.36, 0.1 minus x divided by 4. So it's 0.36 times 0.1 minus x. Let's put up here in B1 what the value of x is. And I suppose we could divide by 4, but let's actually, we'll put a times here. I guess I have too many parentheses. Put a parentheses here. All right. 0.36 times 1 minus x, that's that cell up there. Let's just multiply by 0.25. 0.25, and there it is. So that's the equation. So depending upon what value of x we put in here, let's put in a value of 0, it solves it for 0.9487. There it is, 0.9487. So remember, that was the value. When we ignored x in here, that was equivalent to putting x equals 0. For that, We got 0.949 times 10 to the minus 2. That's what Excel gets. Okay, sounds good. Now, look at this. I'm going to copy this down. So now I'm taking the square root of B2, which was the value of x it got when it took 0. That's kind of cool. So that's the value for that value of x. Now we have this value of x. We copy this down one more time. We have another value of x, 0.8406. There it is that way, and we just gave up here. But in Excel, well, let's not give up. Let's just keep copying this down. All right, so 0.02, 0.08, 0.03, 0.07. See, it is sort of converging. And let's keep going here. Let's keep going here. Copy it down. Let's do, say, copy it down here maybe to 20 times. Oh, look, 5960, 5960, 59. Well, let's just keep going. I mean, it's easy to calculate. Just go down to 100. So we're doing 100 iterations just by dragging this down. Oh, look, it's 0.06. So it converges. Unless we didn't have to go down that far. Let's go up further. Looks like it's converging to 0.06 after about 34, 35 iterations. All right, is that what we got when we did the quadratic equation? Let's see. Oh, well, went too far. Yeah, 0.06. Well, there you go. An easy way to solve by successive approximation using Excel. Okay, that's it. Thanks for listening.